Hi guys, this is a very big lesson with a lot of examples, so settle in for a long one. Otherwise, you can always watch it in parts and do it bit by bit as you go. Now, a reminder, it says area review. You have learnt all of these formulas before. This is just practice using them in more difficult situations, or some of them are actually just straightforward situations, but you have seen this before. So these are our first two formulas: area of a rectangle, base times height; area of a parallelogram, base times height. Same for area of a square, because a square is a rectangle. Base times height, that looks like an L. Base times height. All right, the following shape have the same area. Find the value of the unknown. Ooh, how interesting. So, okay, so to find the area of shape 1, we'll call this area 1, we'll call this area 2. So area 1 is going to be x plus 3 times x minus 1. Do you notice anything here? Have we learned how to expand these before? Why, yes, we have. And what we do is we use the boxes method. We have x plus 3, x minus 1. X times x is x squared. X times 3 is 3x. X times negative 1 is negative x. And negative 1 times 3 is negative 3. So area 1 is going to be x squared, 3x, take away 1x. It's going to be plus 2x minus 3. Now let's do area 2. I'll do area 2 in blue. Area 2 is going to be x minus 2, x minus 1. So we'll draw ourselves a little box over here. X minus 2, x minus 1. X times x is x squared. X times negative 2 is negative 2x. X times negative 1 is negative x. And negative 1 times negative 2 is positive 2. So area 2 is going to be x squared minus 3x plus 2. Now it says they have the same area. So what we can do is we can say that area 1 equals area 2. Or we can say that x squared plus 2x minus 3 equals x squared minus 3x plus 2. Now let's combine these terms. So let's put everything over to one side of the equal sign. Try to solve. So first thing I'm going to do is minus the x squared term. Now plus the 3x. And I might leave the numbers for now and just see what happens. We may move it in a second. X squared minus x squared cancels out. 2x plus 3x is 5x. Now I've left on the left-hand side with minus 3 and on the right with plus 2. Now because we have a two-step equation now, let's move this minus 3 to the other side. We have 5x equals 5. Well, if 5x equals 5, what's 1x going to be? We'll cancel out the 5 by dividing by 5, and we get x equals 1. And that's it. We've solved it. X equals 1. Now that's all we needed to do was find the value of the unknown. It's 1. We don't need to calculate the perimeter, calculate the areas, know what the areas are. We just need to find this unknown. And we found it, x equals 1. Put a little box around it to show that that is your answer, especially if you have messy working out like I do most of the time. That way, your answer is really easy to find. X equals -1. Next question. Find the area of the following triangle. Now this one's pretty straightforward, except we are missing a value, because to find the area of a triangle, we use this formula here. Area equals half base height. So we have the height. The height is 8. We don't have the base. The base is missing. How are we going to find it? All right, so what you will notice is that we do have two right-angle triangles. You have right-angle triangle 1, which we will make yellow, and we have right-angle triangle 2, which we will make blue. Okay, now we have two side lengths on each of those right-angle triangles, and we're trying to find the third side length down the bottom. We have a formula that does that for us, don't we? It's called Pythagoras theorem. So let's use Pythagoras theorem, which we know. Are we finding a long side or a short side for both of these? We're finding a short side. So we're going to use a squared equals c squared minus b squared. All right, so let's do the yellow triangle first. So do the yellow triangle. We have a squared equals 15 squared minus 8 squared. A equals the square root of 15 squared minus 8 squared. Let's put that in the calculator. Square root 15 squared minus 8 squared equals 12.6883. Actually, because we're going to be multiplying these numbers, we really don't want to round. We do not want to round. So let's just figure out what is under the square root. 15 squared minus 8 squared is 161. So we'll just leave that as a square root of 161. And we don't want to round anything until the end. Okay? So next, let's do the blue triangle. The blue triangle is going to be a squared equals 12 squared minus 8 squared, which is the square root. Oh, hang on. A equals the square root of 12 squared minus 8 squared, and which is 12 squared minus 8 squared. Oh, hang on. I did something funny. There we go. So A is the square root of 80. Now, this missing length here is the square root of 161 plus the square root of 80. So to find the area, capital A for area, we're going to do half times the base, which is 161, well, square root of 161 plus square root of 80 times height, which is 8. Now, the reason I've left it as the base is square root of 161 plus the square root of 80 is because I don't want to round before I get to the end. Otherwise, my answer could easily be off by a few decimal places. Now it's time to put all that in the calculator. And we get the area equals 86.531. So we'll leave that as 53 and centimeters squared. So when we have a missing side length, if it's a right angle triangle, Pythagoras theorem. Always think if it's a triangle, could I use Pythagoras? Could I use trigonometry? Okay, new formula, well not new to you, but new to this lesson, is our rhombus and kite, half times diagonal 1 times diagonal 2. Now our diagonals, remember, if we have a shape such as this, your diagonals are the lines that go through the middle from opposite corners. They're your diagonal lines. So A lot of information to take in here. A kite is formed on a coordinate plane where the diagonals lie on the x and y axes. So the diagonals, let's draw a coordinate plane. So this will be our x, this will be our y, and the diagonals are actually on the axes. One of the diagonals has endpoints on the line segment AB, where A is 0.5 and B is, sorry, not 0.5, the point 0, 5, 0, 5, and B is 0, -3. So across 0, up 5, 1, 2, 3, 4, 5, this will be the point A. Now B is across 0 down -3. 1, 2, 3. So this will be our point B. So that there is one diagonal. The other diagonal has endpoints on the line segment CD, where C is -2, 0. So we go across -2, down 0, and this is our point C. And then the next point D is 2, 0. So go across 2, down 0, and that is the point D. Okay, find the area of the kite formed. If we were to draw this as an actual kite, I'll use green because I've used almost every other color. Oh, that's messy. Let's try that again. There we go. That is our kite drawn there in green. And we want to find the area of it. So first thing we're going to do is actually find the distance between our 2 points. Now you remember from our linear topic that we have a distance formula. Distance equals the square root of y2 minus y1 all squared. Actually, they're not usually up there, are they? Down the bottom. y2 minus y1 all squared plus x2 minus x1 all squared. Now that comes from Pythagoras' theorem. However, we really don't need to use that this time. Now the reason we don't need to use that is because we can literally, from our diagram, just count the spaces. So for our vertical line on the y-axis, we've gone from the point 5 down to the point -3, and it goes 8 spaces. 1, 2, 3, 4, 5, 6, 7, 8. So diagonal 1 equals 8. Diagonal 2, we'll do in red. We've gone from the point -2 to 2, which is 1, 2, 3, 4 spaces across. So now we can use our two diagonals to find the area of the kite. Area equals half times 8 times 4. Now, if you're doing this without a calculator, you can either multiply 8 times 4 first. 4 8s are 32. Half of that is 16. Or you can pick one of the numbers to half. You can half 8. Half of 8 is 4. And you get 4 times 4 is 16. Or you can half 4 and get 2. Do 8 times 2 is 16. So you only half once. Otherwise, put in a calculator. That's fine too. And that's it. That's the full question. Looked like it was going to be trickier than it was. Now, if they weren't on the axes and you actually had to calculate the distance, that would be a cooler question. But it is nice that they gave you lines that were on the axes, so you could just count to find the diagonals. And the area equals 16. Hang on, I've forgotten my units. Do we have units? No, because we're on the coordinate axis. No, you don't have units. we can just write units squared, 16 units squared. Example 4, find the area of the following rhombus. Now a rhombus has the same formula we just used for a kite. Area equals half times diagonal 1 times diagonal 2. So we've been given the perimeter is 120 centimeters, and one of the diagonals, well, hang on, perimeter is 120, and one of the diagonals has a length of 40 centimeters. Now we also need to know a few other fun facts about rhombuses. Now rhombus is like a square that's been pushed over. So, come on pen, here we go. All sides are equal. Okay. We also know that the diagonals bisect the angles or the corners. So that means, let's draw a rhombus so I can explain what I'm talking about. A rhombus looks like a square, but it has been lent to the side. So all sides are the same. 1, 2, 3, 4. Opposite sides are parallel. So let's add our parallel. Our diagonals, so we'll draw a diagonal here. Oh, that wasn't going very straight. Diagonals bisect our corners. So here and here, they are equal. So that is equal to that. And one other fun fact that we do know about all quadrilaterals is the angle sum. So reminder, angle sum of a quadrilateral is 360 degrees. Okay, so we're going to use those fun facts to calculate the area. So step 1, first, we've been given the perimeter is 120. If the perimeter equals 120 centimeters, we can use that to find one side length. So do 120 divided by 4. When we divide by 4, we'll get just one side equals 30 centimeters. So let's add that fun fact to our diagram. 30 centimeters per side. Okay, now one of the diagonals is 40 centimeters long. I don't know which one it's going to be. It's going to be the shorter one or the longer one, but I'm going to draw it on the longer one because I've already drawn. Actually, I'm assuming it's going to be the shorter one. I might be wrong. I'm going to draw it on the longer one only because I've already drawn the longer one. Okay, so now what I'm going to do is draw my other diagonal. So if the whole line is 40 going all the way across, that means each half of the line is 20. So we've got 20 centimeters here, 20 centimeters here. And another fun fact we didn't write, diagonals bisect at right angles. So this here is a right angle. All those 4 angles are right angles. Okay, so if we're looking at my diagram, I'm going to extract this triangle here. Okay, so I'm going to redraw that bigger here. And the reason I'm doing that is so we can easily see what I'm doing. This part here, that's 30. This is half of the diagonal, which is 20. And this we don't know, we're going to call it x, because when we don't know something in algebra or in math, x is always a good letter to use. Okay, now we can find the missing side length. And how can we do that? We can use Pythagoras, because Pythagoras is everywhere. And now we're finding a short side, so we're going to use a squared equals c squared minus b squared. You guys are going to be so good at Pythagoras by this topic. A squared equals 30 squared minus 20 squared, which is the square root of, I'm just going to put it in the calculator straight away there. 30 squared minus 20 squared is 500. Does 500 go? I don't think it does. 500? No. So we're not going to calculate it or estimate it. We're going to leave it in exact form, which means we're going to leave it without rounding it. So we're going to leave it as a square root of 500. So that means this length here, x, is the square root. Oh, how can you write on such a weird angle? Let's try. The square root, there we go, of 500. And that's that there. Square root of 500. And we have two of those, don't we? 500 there. Okay, I hope my diagram's not getting too messy. I hope you're following along. We can now finally calculate the area of the rhombus using our two diagonals. So I'll go here. The area of the rhombus is going to be half diagonal 1 times diagonal 2, which is a half times diagonal 1 we know is 40. Diagonal 2 is 2 lots of root 500. So we just need to put that all in the calculator now. Oh. Half times 40 times 2 root 500 is 894.427. So round it up to 43. And that is in centimeters squared. So you're probably noticing a trend in these questions. You can't just go straight into what's the answer. You need to first figure out what do we need to find the answer. What is missing? What can I find first? All right, example 5. So this has two parts. We're finding the area of a circle and the area of a sector. Now, these ones, the only tricky or interesting thing to make it not so straightforward is this word here. Find the exact area of the following shapes in terms of pi. So that means we don't want to round. So if it says exact, no rounding. So if you've got a square root or you've got pi, you leave it as a square root or you leave it in terms of pi so that we don't have to round anything. All right, we're going to use our circle formula first. Area equals pi times 4 squared. Now that's going to be pi times 16, because 4 times 4 is 16. However, when we write things, just like in algebra, if we were to write a term, we would write 5a or 17x. You always write the number and then the letter. So in terms of pi, pi is kind of like your letter or your pronumeral. So we have area equals 16 pi. For part B, we're going to be using this formula up here, theta over 360 times pi r squared. So we've got area equals theta, which is 60, over 360 times pi times 9 squared. Area equals, now 60 over 360 simplifies. Well, first we can cancel out the zeros. and get 6 over 36. And then we can divide both of those by 6, and you get 1/6. 1/6 times pi, and 9 squared is 81. All right, now, does that simplify nicely? What is 1/6 of 81? 13.5. So we get area equals 13.5. And I got that by multiplying a 6th times 81. And we get 13.5. And then we just write our pi on the end. And that is in exact form. Example 6. Given that the area of a semicircle is 360 meters squared, find the radius of the circle. Let's start by drawing ourselves a diagram, because that's always helpful. I'll just draw it in this space here. Now we've got a semicircle. We know the area is 360 meters squared. We want to find the radius. Now remember, the radius goes from the middle to the edge here. Now the other thing we know about this is if we were using our formula for area, because it is just a sector, is theta over 360 times, oh, not 2 pi r, that would be perimeter, times pi r squared for area. Now the theta is this here, which is a straight angle 180 degrees. So area equals 180 over 360 times pi times radius, which we don't know, squared, but we do know area, don't we? So instead of area, we can write 360. 360 equals 180 over 360 times pi times r squared. Okay, now, first thing we're going to do is let's simplify this fraction. It doesn't have to be 180 over 360. We can write it as a half. 360 equals a half pi r squared. You can write the times, you can leave the times, like the symbols. Either way is up to you. Next, let's simplify. So pi times r squared, and we've got our half. To get rid of a half, multiplying by a half, the opposite of multiplying by a half is dividing by 2. No, well, it's the same, sorry. To cancel out a times by a half, we're going to divide by a half. Now remember, when we divide by a fraction, if we were to divide by a half, we flip and multiply. Same as timesing by 2 over 1, which is the same as timesing by 2. So to cancel out times a half, we're going to times by 2. And we get 720 equals pi r squared. Next thing we're going to do is divide by pi. Now, we're not going to put that in the calculator yet, because then we will be rounding and getting a decimal answer. So we're going to leave that as 720 over pi equals radius squared. And last step is we're going to take the square root to cancel out our squared, and we get r equals the square root of 720 over pi. Now that would be an exact form, but this one doesn't say that, so we're going to calculate an answer. So square root, fraction button straight away, 720 over pi equals 15.138, so we'll write 15.14 meters. That is our radius. Now if you wanted to check it to work forwards, we could sub it back into our equation and check. So let's just check. So area equals theta, which is 180 over 360 times pi times 15.14 squared. Chuck it in the calculator and see if you get 360, or your answer rounds to 360, because remember we've rounded our answer. So when you put it back in the calculator, damn it. When you put it back in the calculator, your answer may not be exactly 360, but may be very, 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 very close. So I got 360.057, which is inaccurate because of our rounding. So it's approximately 360. So we did it. Woo! All right, next question. Example 7, find the exact area. So this is another exact question, which means we need to leave our answer in terms of pi or in terms of square root of the composite shapes. All right, so remember we've got composite shapes. We break it up into two parts. We've got area 1 and area 2. Area 1 is just a rectangle, so we're going to do area 1 equals base times height. Area 1 equals 20 times 35. Area 1 equals, now because this answer won't need rounding, we can actually calculate it, is 700. Area 2 is a semicircle, so it's going to be theta over 360 times pi r squared. Now our radius, down here we've got this whole length is 20, so this whole length here is 20, but our radius is half of that. It goes from the middle to the edge. So radius is going to be 10. So area 2 equals 180 over 360 times pi times our radius 10 squared. Now, we don't want to calculate all of that because it'll give us a rounded answer and we want it exact. So we've got area 2 equals a half, as fraction simplifies to a half, times pi times 10, which is 100. Now we can combine a half times 100, and a half times 100 is 50. So area 2 equals 50 pi. All right, now to find the total area, we're going to do area 1 plus area 2, which is 700 plus 50 pi, which actually that's as far as we can go. They're not like terms because only one of them is in terms of pi, so that is our answer, 700 plus 50 pi millimeters squared. We'll put all that in a bracket, so that is all our answer and it's all millimeters squared. All right, part B. Draw a little line here to show that was A. Down the bottom we're going to do B. So we've got, this time it's going to be a takeaway because it's the shaded area we're going to find, all this space here. So we're going to do first, area 1 is our rectangle and area 2 is going to be our circle. So area 1 we find by doing base times height, which is going to be 14 times 6, and 14 times 6 is 84. Area 2 is a circle. We find the area of a circle by doing pi r squared. Now it has also given us the diameter and not the radius. So we're going to have to do pi times 2 squared. And 2 squared is 4, so it's 4 pi. We always put our number before our symbol. 4 pi. Now our total area is area 1 plus area 2. So area equals 84 plus 4 pi. And once again, we can't simplify that. So it's just 84 plus 4 pi centimeters squared. Okay, last example. Now this is our formula for the area of a trapezium. Height over 2, a plus b. Height is the length between the two parallel sides. So sometimes your trapezium will be on its side. So a trapezium looks like this. two parallel lines, and they're joined by two lines. Now, your parallel lines could be vertical. Gosh, they're not very parallel. Let's try that again. If your parallel lines are vertical like this, and they're joined, well, then your height is going to be across instead of up and down. All right, create a straight line between C and D. So here's C and D. Please make your line straighter than mine. As you know, my pen is broken, so it doesn't do straight lines very well. Use the trapezium formula to approximate the shaded area. So we're going to find this is our trapezium. Down here and here are our parallel lines. And we have our two joining lines. Okay, so step one, we need to write our formula. Then we're going to have to find all the bits and pieces from our formula. Now, this is a really common use of the trapezium formulas to approximate areas that are almost a trapezium. So our height is actually, this time, going across. This here is our height. And we can read it straight off the bottom. It goes from 1 till 9. So that is 8 across. 8 over 2, A plus B. So A and B are our parallel lines. Now A, we can see, is 2. It goes from 0 to 2. So from 0 to 2 is 2. B goes from 0 up until this point here. So what are they going up by? 1, 2, 3, 4, 5 goes up 5 between two numbers. So we're going to be going up by 0.2s. So 1.2, 1.4, 1.6, 1.8. So it's 1.4. So the area is, now it's just time to put it all in the calculator. 8 over 2 bracket 2 plus 1.4. And we get 13.6. Now we don't have units again because we're once again on the Cartesian plane. So we go units squared. 13.6 units squared. And that is our approximate area. And that might be one of our longest videos ever, but we are done all of our 9 examples.